Okay, we know we can express this area using an integral from -2 to 2 of the function with respect to x is how we first learned about this stuff. We know, we said, oh, use this integral because we need to take the antiderivative, and this is how we can find the actual value. Take the antiderivative. We don't need the plus c because we're going to be subtracting an end kind of starting position minus a beginning starting position. And we get 8 minus 8/3 minus -8. This is -8/3, so that'll be plus positive 8/3. And you end up just like kind of doubling up. So this is 16 minus 16/3. 16 is 32 48/3. 32/3. Cool. So it's like review here. But the new stuff that we were introduced with last class was that this doesn't just mean take the antiderivative. This actually means an infinite sum. And what we are taking an infinite sum of is a bunch of rectangles, heights times widths. So that you guys as students understand the two ways of thinking about this integral, the College Board requires you to understand how you can write this area using an infinite sum, but without using an integral. So what does that mean? It means you need to be able to write this limit as n approaches infinity of the sum. We always say I starts at 1, we go to n. I'll explain why I is starting from 1, going to n. And again, it's infinite sum of heights times widths. Unfortunately, it's not as easy as just saying 4 minus x squared times dx. So don't write that down. Okay, it's more involved than that because what this does not have, this infinite sum, is the -2 to 2 factored into things. Okay, so we have to do a little bit more work on this side. We're not going to use this very often, but it's just required for you to know so that you understand that like integrals can mean antiderivatives and they also can mean infinite sums. Okay, so we're going to say, well, it's some function values, f of x sub I, and the sub I is where we're going to incorporate the -2 to 2, as well as times widths, the delta x's, which turn into dx as n approaches infinity. We're just keep it at delta x, and these are our heights and our widths. Okay, now to incorporate the -2 to 2, here's what we're going to do. We're going to replace x sub I by saying, okay, the x's we use in our function are going to start at our starting point A. In this case, it's -2. And then to tell which function or which x value to plug into my function, we need to add some sort of delta x so that I get to the next value, use that value as my first rectangle. And then I'll add another delta x. So I'd add 2 delta x's to get then the next height. And then I'll add 3 delta x's. And this is just an example so that I get there. So we need to add a multiple of my delta x's to plug in certain x values into my function. And this is where the -2 and 2 are going to come into play. Now, what is delta x? Well, we introduced to it ourselves to it last class. It is the width of a subinterval. To find a width of a subinterval, just find the distance of your entire subinterval or your entire interval. There's the a and b getting incorporated into things, and then divided by the number of objects that you have. So in this case, b minus a is 2 minus -2 divided by n, so that's 4 over n, which means this is 4 over n. Okay? So we will now rewrite this so that it's no longer x sub I to incorporate the boundaries and to understand that we are doing a right Riemann sum. We will do a plus I delta x times delta x. Don't worry, we're almost there. We're not done yet. The last thing you need to do is replace f with what f of x is actually equal to. And this is what your final answer would look like when you see a question like this on your test. The limit as n approaches infinity of sum I starting at 1 going to n of 4 minus x squared, where x is -2 plus 4i over n. Just rewrote those in a different order. That's your height times your width, 4 over n. What do you guys think? Little giggles here, huh? Because it's complicated and it's like, what? And it's like, do we need to use this? No, we're not going to use this in the future. But it's required for you to know that this integral also means this. Okay, let's talk about this. Where does this come from again? Okay, so we have heights times widths. We're using an infinite Riemann sum, right? Because we're talking about if I use an infinite amount of geometric shapes over an interval, my approximations will keep getting better and better and better, and they're approaching the actual value. So we're just going to use areas of rectangles, heights times widths. The heights come from the function 4 minus x squared. But we don't just pick random x's. We need to know where we start and where we go. We start at -2. And then we will pick another x value, but it's just not a random one. It's going to be a width, a delta x away from my starting point. We know that when we're taking a sum, we're plugging in 1, then 2, then 3, then 4, then 5 into I. So if delta x ends up being, I don't know, like 1, then I'd say, okay, plug in -1, which is -2 plus 1, to get this height, and there's my height. Then I multiply by delta x to get the width. Width, height, there is my first rectangle. Now, why is it a plus I delta x? Because for the next rectangle that I'm summing up, I'm going to be adding another delta x. That's 2 delta x's. So -2 plus 2 delta x's. Now I'm at this x coordinate. I plug that into my function. I got that height. Take that height times this width. You get this area. Hopefully that makes sense to you, why we have a plus I delta x and why delta x, the width, is b minus a over n. You don't have to understand that, though, because the only questions that you'll be asked to do is to take this and write this area as an infinite sum. And if you're able to do that, you may see a question on the AP exam that has something like that. So why don't you guys try with this? You can do it. It's not hard. It's really just like plugging in values into the formula. If you understand x sub I is 2 plus 3i over n, if you understand delta x is 3 over n, you just need to replace f with the log function and replace x with 2 plus 3i over n and replace delta x with 3 over n. I don't think it's super hard, but yes, does it look confusing? It is. Are we going to be doing anything with it? Actually, no. You just need to understand that here is an infinite sum and this is equivalent to this infinite sum. Now, you could probably guess why. We don't focus much on doing this stuff. And mathematicians said, let's not write down these infinite sums. Let's instead use this notation. Does it make sense why we're using this notation? Okay, good. That's why we're using this notation. That's why we're going to understand how to do things. Now, I can't evaluate this why without a calculator. Why not? You don't know how to take the antiderivative of the log function. Okay? So use your calculator. Maybe there is some way to do it using this, but I don't know how to do it. So anyways, that's it. Now, the rest of the lesson is on integral properties. Some of these you already know, so it's just review. We understand that when we read an integral, that order matters. And we might understand better why, if we have an area above the x-axis, our area is positive, but if we have an area below the x-axis, our area is negative. Why is our area negative below the x-axis? Because the height of all of the infinite sums of our rectangles, heights times widths, the heights are negative. The width, since I'm going from A to B, from left to right, the width is positive. It's a positive x direction. That is why that area is negative. If you think about it as an infinite sum of heights times widths, it should make better sense to you now. Okay, going from B to A. Remind your neighbors, what is its relationship to A to B? Not inverse. It's the opposite. Opposite is what we're looking for. Opposite. Inverse is not opposites. It's not reciprocals. Inverses are just like the function that undoes the other function. E to the x is the inverse of log x. They're not opposites of each other. They're not reciprocals of each other. That's okay. It's a common mistake. People mistaking inverses with reciprocals with opposites. So it's okay. Now, why is this area from B to A negative? You should be able to understand more why if you think about how this is an infinite sum of heights times widths.
The width is negative.
Why is the width negative? Yeah, delta x. If you think about this as 1 to 4, but we're going from 4 to 1, delta x is always like b minus a over n. Well, b is the ending point minus a over n. This is negative 3 over n. That delta x, which turns into a dx as n approaches infinity and it gets infinitely small, it's going to be an infinitely small negative value. So heights times widths, the widths are negative. Heights are positive. Okay, so that's a negative area. This is a positive area. We've already talked about, and just reminding, what is an integral from A to A?
0.
And why is that?
Because there's no width.
So which part of this is 0?
Yes.
The dx is 0 is exactly right. The height exists, but the width, if we're doing heights times widths, is 0. Okay, to some more integral properties. The first one is if we have a constant times a function. It's very similar to antiderivative rules and derivative rules. We are able to pull the constant out and then just multiply by the area under the function. This may help simplify some things sometimes, This one seems very logical, that if I know this area is 2, and then I multiply it by 3, this area ends up being 6, and you would be correct. And you could see if I multiply all these function values by 3, it creates these function values. I end up with a triangle, base length 2, height of 6, so that's 6 as well. So most of you will kind of skip this step and just take the number and multiply by the area under the function. Just be careful because it won't always be the case. This one's an easy one to understand. We have an integral from a to b plus an integral from b to c under f. Go ahead and discuss with your neighbors what do you think that's equal to. Yeah, a to c. That's not bad at all, right? All right. Now, this one is very, very useful. I will use it for pretty much all of the examples we do once things start rolling. If we are adding or subtracting two different functions, sometimes it's beneficial and extremely useful if you split up these functions and their areas into two different integrals. Okay? It's not necessary, but sometimes it's very helpful, especially when we start doing some of these integral properties. Now, let's go and look at this one. If we think about the other rule, where it's the integral from a to b of k times f of x, I told you, you can just take that k and multiply it by the integral. So it's just very logical. Take the area, multiply it by k. We're good. Adding, though, a constant is not as easy. We might think, oh, okay, this area under f from 1 to 3, base length 2, heights of 1 and 2, this is 3. Well, let's say I add 3 to it, we may think that this area of f of x plus 3 must be 6. But that's not correct. And there's two ways for you to understand this, and before we get into this, let's talk about just the area under a constant. Like, let's say this is y equals 3, and I ask you, what is the area from 1 to 5 under y equals 3? There are two ways to handle this. One is using the fundamental theorem of calculus, which you already know, and the other one is just using logic and geometry. What would be the area under y equals 3 from 1 to 5? This is 12. You can either think of it as a height times a width, and the height is consistently 3, and the width is 5 minus 1, which is 4. That's 12. What's the alternate way of getting 12, besides just 3 times 4? Yes, taking the antiderivative and using the fundamental theorem of calculus. The antiderivative is 3x. Plug in 5 and 1. You get 15 minus 3. Okay, that's the other way of getting 12. This is using the fundamental theorem of calculus and using the antiderivative. So the area under a constant is not just like the number. The area is either the constant times b minus a, or if you do the fundamental theorem of calculus, it ends up as kb minus ka. Okay, so since that is the case, if I take the area from 1 to 3, under f of x plus 3, we think, oh, just add 3 to 3 to get 6, but no. Using two properties, the first property is saying you could split this up into two different integrals, and then reminding yourself that when you're adding a number, you're just not adding the number, you're adding a rectangle worth of area. You get, this one was 3, we found that geometrically, but this is not 3, this is 6. This is a rectangle, height 3, width 2, or this is 3x from 1 to 3, which is 9 minus 3. This is 6. So the answer is actually 9. So overall, what am I telling you? You can find the area from A to B under F, but don't just add K. Add a rectangle's worth of area with a height K over your interval, either using the fundamental theorem of calculus or not. Okay? Now there's another one. Fit somewhere in your notes here. If I asked you to do that, what would you do? Discuss with your neighbors. Good if we're thinking, you know what, I'm not sure, it's not a horizontal line. I should just take the antiderivative, plug in 1 and 5, 25 minus 1, 24. But I'm going to tell you there's another way to get this. And it might help you, it actually might save some time. We could do this geometrically. Why? Because 2x is a straight line. And when we have straight lines, we can use geometry. When we have curves, we have to use the fundamental theorem of calculus. Well, if I have a straight line between two values, but it's not a horizontal line, it's a curve, what shape is created? A trapezoid. We could use a formula for a trapezoid for a diagonal line, not a horizontal line. Where are we going to get that formula from? Well, remember, it's 1/2 our base length and then our heights. Well, our base length is going to be, sorry, this is 1 to 5. Our base length is the 5 minus 1. We can see that from our integral. So 4. Where do I get my heights from? Yeah, in this case, though I don't ever want to see you do this in other situations, you can plug in 5 in here and plug in 1 in here to see that the height at 1 is 2 and the height at 5 is 25. Sorry, 10. So 1/2, 4, 2 plus 10. Am I going to get 24? Yep, 12 times 2, 24. So maybe you want to do that in the future, maybe. But I think it's pretty easy to do just x squared from 1 to 5. Okay? Remember, curves, you must take antiderivatives. Straight lines, you can use geometry. All right. What you'll find is for the remainder of class, it's just examples of what you're going to see. And it's just making sure you understand your properties. You will be given information. You will not be given expressions or equations. You will be told, hey, the area under F, whatever it is, from 0 to 5 is 10. And the area under F from 5 to 7 is 3. That's it. But just using those two pieces of information, you're going to be able to answer all 6 of these questions. I'd like you to change the one on the bottom right to a minus 2x, just for fun, because we have fun here. All right. Second one, easy. 7 to 7, what is it? Third one, or really like the fourth one here, 0 to 7, easy. What's 0 to 7 of f dx? 13. How'd you get that, Mr. Berthune? Yeah, you got 0 to 5, you got 5 to 7, this is easy. Okay? 5 to 7, this one is easy. Okay? The constant can be pulled out. You have the area from 5 to 7, 3 times -3, -9. Okay? The other ones is where students get tripped up. For example, the one on the top right, the integral from 0 to 5 of f plus 3. Many students will answer 13, and they're wrong. Why don't we do this one first, and then we'll talk about the ones when we're going from B to A and how we would handle those. we should get 25. There we go. So, if you remember, and what I will suggest you use, very useful, is the fact that you can split this up into two different intervals. 0 to 5, you know, is 10. Y equals 3, horizontal line at y equals 3. From 0 to 5, it's a rectangle, width of 5, height of 3, 15. This is how we get the correct answer of 25. So do not assume that, like the negative 3 times, we're going to just add 3. It's not going to be the case. Now, when we deal with negatives and going from right to left, what I would always suggest, I think it will help you, is step 1. Whenever you see right to left, immediately flip it to left to right, but just make sure you say, I'm taking the opposite of whatever answer I get. Whether or not there's like 1 thing, 2 things, 3 things, like once we go down to this one, do this first, okay? Now what I'm able to do is take out this negative 3, but that negative 3 and this negative will make a positive 3. So it's just positive 3, 0 to 5, f of x. 0 to 5 is 10, so this is positive 30. Okay? If you start thinking, oh, it's right to left, but there's a negative, like, people make mistakes, wires get crossed. So just keep it simple, write out a couple steps. It will help you if you write those things out. Okay? Everybody try the one on the bottom right, and let's see if we can get this. So I'm thinking it's positive 36. Positive 36. Anybody else get positive 36? Change yours to negative 2x. Anybody get 36? All right, now we're getting it. Okay, good. My first step would be to flip the boundaries so that it's from left to right. Know that I want to get the opposite of my answer from right to left. The next thing, I would split this up, and I'd be careful. I got 0 to 7 of f. Now, you could either plus an integral from 0 to 7 of negative 2x, or you could say it's just minus an integral from 0 to 7 of 2x. Both of those are fine. Probably actually easiest to use the fundamental theorem of calculus here. Antiderivative of 2x is x squared. Plug in 7, plug in 0, 49. I can easily get that just by thinking, rather than potentially using the trapezoidal formula. 1/2 base length of 7, heights of 14, and 0. I don't know, maybe. So we found from a previous problem that this was 13. This is x squared from 0 to 7, so that's 49. I subtract those two numbers. This is negative 36, but I remember to take the opposite of it at the end to get my answer positive 36. Okay? Okay, moving down to the next set, same deal. But now we're talking about f and g. very, very simple, this first one, if you realize, oh, I could split this up into an integral of f plus an integral of g minus an integral of 2. Now, again, the minus 2, you don't just subtract 2 from the area under f and the area under g. So the answer is not 6. There's more that you need to subtract. All right, go ahead and figure that one out. We should get a big fat 0. 2 to 6 is 10. 2 to 6 of g is negative 2. That's 8. Then 2 to 6 of 2, it's very quick to use geometry. Height of 2, width of 4, that's 8. So we got 10 minus 2 minus 8. That's 0. All right, try the one on the right real quick. Looks like positive 22 is the answer. Okay. Keep going. So we dealt with a situation where I'm giving you stuff about f, then I gave you about f and g. Now I'm giving you information about f, g, and f minus g. All right, do the one on the left. Probably our first instinct is to split this up, and it's good that we are doing that. But then we realize, oh, I got to do a little bit more work to figure out what the integral from 0 to 5 is of f. You could pull this 3 out, then divide. 0 to 5 of f is 2. So this is 2, this is 7, this is negative 5. Now, what would be the answer to the one on the right? In this situation, splitting up does not help you. Yeah, that's the key. Answer is negative 7. How? You found 0 to 5. You have 3 to 5. You're wanting 0 to 3. 0 to 3 plus 3 to 5 equals 0 to 5. They're little puzzles, these questions. They're fun. We're having fun here, right? Don't know what this is. This is 2. This is negative 5. Subtract 2, you get that this is negative 7. Okay? Finally, more things that we've kind of dealt with. I want us to include something else on this last example. Please change everything to f prime. Change all this to f prime. And again, if you're adding a constant, you're not just adding 3. Okay, so this first one I would say, okay, from 5 to 7, f prime of x plus 5 to 7 of 3. Take the opposite of that answer, because I'm wanting the answer from 7 to 5. 5 to 7, this area down here is -2. So I got minus -2, 5 to 7 of 3, rectangle, height 3 with 2, this is 6. So this would be 4, but take the opposite of it, my answer is -4. 2 to 2, 0. Regardless of whether we are adding anything else, the width is 0. Heights times width. Here, if you have an absolute value, just know that all the values of the areas that were negative, the displacements that are negative, will become positive. We've dealt with this before when we did displacements, and this was a velocity graph. So 3 to 7 would be 2. This is 1, and this would be positive 2. So this is 5. But now, one extra question, which is another review question. I want you to find f of 5. Now, I want you to find f of 2 given f of 5 is 3. How would you do that? This is probably the most important question that we're doing all lesson, because it's a review question. Yep. Yes. This value often remembers an unknown ending value equals a known starting value. But we've always been used to displacements being from like left to right, from a smaller value to a larger value, but not always. We would do an integral from my starting to my ending. In this case, unknown end, that's 2, known start is 5. What do I need? The area under f prime. Think of this as position as x. This must be v to find displacement. So in this situation, I have f of 5 is 3, but then I'm not going to add the area from 2 to 5, which is 5. I need to subtract the area from 2 to 5 because I'm looking for the displacement from 5 to 2. So f of 2 would be -2. Okay? This is probably the most important formula that we learned so far this semester, is this application of the fundamental theorem of calculus, finding unknowns given knowns and areas under derivatives, which will give us displacements.